One of the things that happens in air conditioning systems is that we have the adiabatic mixing of airstreams. And when I had mentioned that we needed a certain amount of fresh air per person in a lecture classroom, what happens is they recirculate part of the air and bring in fresh air and mix them together. So it's an adiabatic mixing problem, and we want to be able to determine the output of that. So what we have with adiabatic mixing is I have two air streams coming in, and I'd have one in state 1, one in state 2, and we'd have m dot A1, T1, omega 1, the same thing here, m dot A2, T2, and omega 2. And very often, one is recirculated air, the other is fresh air, and then we're coming out here at m dot 3. M dot A3 is equal to m dot A1 plus m dot A2. We'll have a T3 and an omega 3. And in this case, Q dot is equal to 0, and there's no work done. We're just mixing the streams together. And so what I wanted to do is let's mix two streams. I'll give you the information about them. We'll find out the values and see what this looks like. And so let's say that m dot A1 is equal to 100 pounds mass per minute at 75 degrees Fahrenheit and 60% relative humidity. We have H1 is equal to 30.4 BTUs per pound mass, and omega 1 is equal to 0.0112. So I have what those values are. We'll have that m dot A2 is equal to 75 pounds mass per minute. It will have 65 degrees Fahrenheit and 50% relative humidity. And we have that H2 is equal to 22.8, and omega 2 is 0.0066. So we look those up, and most often you wouldn't be given pounds mass per minute, you'd be given the CFM, and then we divide by the specific volume. But I wanted to speed that process up, so we look at that. And we see here that m dot A3 is equal to 175 pounds mass per minute. So we add the mass flow rates together as we indicated here. And now what we do is we do a first law right here. So we have the stuff going in and stuff leaving. We do a first law analysis on that. So if I do a first law, I have m dot 1 H1 plus m dot 2 H2 is equal to m dot 3 H3. And so I have 100 times 30.4 plus 75 times 22.8 is equal to 175 times H3. And we get that H3 is 27.1. So we have what that value is, but if I look at the psychometric chart, here's the value of H. So it's along this line somewhere, so that tells me one thing. This is my H of 27.1. So I have that, but I don't know where the other point is. So I need to find omega. So I'm going to find omega and find out where the intersection is. So now if I do a conservation of mass of water, I have m dot 1 omega 1 plus m dot 2 omega 2 is equal to m dot 3 omega 3. And I can solve for omega 3. So 100 times 0.0112 plus 75 times 0.0066 is equal to 175 times omega 3. And I get that omega 3 is 0.0092. So if I go in, So now if I know this value of enthalpy, so I know that value of enthalpy and this value of omega, so now I can go in at that value of enthalpy, this value of omega, and X marks the spot, and you'll find that this is about 70 degrees Fahrenheit and 60% relative humidity. So the output, so it's state 3, this is what we would have. Now, there's a sneaky little thing going on here that I'd like to show you about so I could make your life easier, which often doesn't happen. So now, let's look at the psychometric chart now. So if I look at the psychometric chart, and I plot 1 and 2. So here's state 1, here's state 2. And I draw the line between them. So if I look at the line between them, all I need is either omega or h to find it. So state 3 is going to be located along this line. State 3 will be along line 1, 2. So all I need is either the h or the omega to locate the point. So if you draw this on the psychometric chart, put that in, find either one of these, that will locate where state 3 is. So that's the rare example of my making life easier for you. And so now so that's with this using the psychometric chart. I wanted to talk about something called evaporative cooling. And so this is a way for us to use evaporation to cool and humidify air. And we see this being done, it can be done in sports games. You'll see players and they have a big fan and people are sitting there, it's hot outside, they're blowing air. They're doing more than blowing air, they're humidifying the air as they blow it. So let me show you what this means. So we have evaporative cooling. And sometimes these are called swamp coolers. So basically, it's an inexpensive way to cool down your air. And as I said, you can see it at ball games, etc. So let's see what the idea is. So the idea is that if I have, let's say it's 95 degrees dry bulb and it's 25% relative humidity. So it's hot and dry. And despite what people say about dry heat, it's still hot. That's been my experience, is that hot is hot. And so I have some water here. So I'm going to have water and I'll have a fan. So I'll have a fan and I'm going to have, here's state 1. So it's going to come in, I have the fan going on, and I'm going to come out here, and perhaps I'll be at 75 degrees dry bulb and 60% relative humidity. And what happens on the psychometric chart is that I'm starting here at 95 and 20%. So I'm starting here at state 1. And now what I'm doing is I'm evaporating the water. To evaporate the water, it has to take energy from somewhere. It takes it from the dry bulb, it takes it from the sensible heat part of the air. So now my line of constant enthalpy, H equals C, and I'm basically driving up this line until I get to our state 2. So here's state 2. So I'm cooling down the air, so the air is cooler but more humid. But in terms of temperature, I've been able to drop it 20 degrees by humidifying it. And so this is evaporative cooling. And so in homes, you could do this where you just are humidifying. Of course, you don't want to get moldy in there, but it becomes an inexpensive way to provide this. And as I said, on ball games, you'll see football games, etc. You'll see where this happens. Now, another place we use evaporative cooling is in cooling towers, and I will refer you to a figure that is done better than mine, but I'll explain it qualitatively here. And there's a good example that provides the analysis for this. So now cooling towers. So if I look at cooling towers, and this is figure 16.34. And what happens is these are used in power plants, and in power plants there's circulating water that comes from the power plant. We need to cool it down. It has a purpose in there. So we're going to have a cooling tower, something like this. Let's see. So we have air. So we have atmospheric air coming in, and it's going up. So it'll be pulled up, and we have a fan here. So there's a fan that's going to circulate and cause this. We have water that comes in. And so we have water at about 100 degrees Fahrenheit. The atmospheric air, in the example in the book, let's say we have 80 degrees Fahrenheit and 60 wet bulb. And so P is about 30%. And we're going to have liquid down here. So what happens is the water comes in and is cooled. So the air comes in and we have this process going on, except now we're able to cool the water and we're heating up the air. So the air would come out of here, let's say at 90 degrees Fahrenheit and 90% relative humidity. So it's very much saturated. So the saturated air that we talked about earlier very much happens, but we have this circulation coming out. The water cools off as it comes down, and we have to have some makeup water. And then this is water returning. So I have the water returning, it goes back and goes into some plant, and then comes back out like that. So we have that happening. So for homework, do 1645 star, and the example 1611 goes through an example doing this.